this video, we're going to look at section 10.5 and section 10.6. So section 10.5 is really short. It's just talking about the relationship between hypothesis testing and confidence intervals. So as a reminder, when we looked for a confidence interval, here's the formula that we used. And remember that what we've got here is the estimator plus or minus the critical value times the standard error of the estimator. And then in section 10.3, we looked at the two-sided hypothesis test. And what we did was we constructed the rejection region here. So in terms of the rejection region, what we were looking at was if we were to draw a standard normal curve, since Z follows the standard normal, what we were saying is if the absolute value of Z fell outside of the endpoint Z alpha over 2, then we would reject. We could also say, instead of looking at the absolute value of Z, we could look at negative Z alpha divided by 2. And if Z fell to the left of this value, then we would also reject. So what that tells us is if Z falls anywhere between negative alpha over 2 and Z alpha over 2, then we're going to fail to reject. And so if the value we find falls anywhere here, we're going to fail to reject. And so notice that's exactly what we have right here. If our test statistic falls anywhere between those two endpoints, we fail to reject. So next what we're going to do is substitute in what Z is, and you'll see that right here. And then from there, we're going to actually solve for theta naught. And the reason for that is under the null hypothesis, theta is equal to theta naught. And so you'll notice down here we've isolated theta naught by itself. And if you look here, this is exactly what we got for the confidence interval that we calculated before. The only difference is in 8.3 in the center of the interval we had theta instead of theta naught. But remember, under the null hypothesis, theta is equal to theta naught. So what this tells us is we're not going to reject if theta naught is in the confidence interval that we calculate. And the reason for that is the confidence interval that we calculate gives us a range of reasonable or plausible values for theta. And so if the value of theta naught is inside of that interval, then it's a reasonable value and we don't want to reject it. If the interval that we find lies entirely in the alternative hypothesis, then that would mean that we have evidence in support of the alternative, and that's when we would reject or accept the alternative. And you can read a little bit more in your book here about the one-sided tests, and those also correspond. All right, next we are going to look at section 10.6, and section 10.6 should be a pretty easy one. This one is going to be 100% review from your intro stat course. So in the previous sections we looked at hypothesis tests using rejection regions, and when we did that I had you all review a little bit about p-values just so you could see p-values, which you're familiar with, give the same results as the rejection region. And so in this section we're going to formally look at p-values, and so again this should be pretty much all review. So just recall that alpha is equal to the probability of a type 1 error. That is what we call the significance level. And we used alpha previously to find our rejection region. And so note, it's possible that when we collect data, it might lead us to reject the null when alpha is equal to 0.05, but not reject when alpha is equal to 0.01. So in other words, we could find two different rejection regions, one for 0.05 and one for 0.01, but our test statistic we found falls between the two. The same thing can happen with p-values. So if you'll recall, in your intro stat course, you might find a p-value that was significant at the 0.05, but not at the 0.01 level, and that does happen. So for that reason, what we'll do, so usually we only report our conclusions in the alpha level used. So two different statisticians could report opposite conclusions. So what we instead do is typically we do go ahead and report what the p-value is. And so we've got the definition here. The p-value or obtained significance level is the smallest value of alpha for which we reject the null based on our data. And so the smaller the p-value, the stronger the evidence we should reject the null. So, and the p-value is going to give us much more information than just saying we reject or we fail to reject. And so what you'll want to do is, if you were writing a journal article, you would still say our results are significant, but oftentimes what you'll see right after that is in parentheses, you'll actually see what the p-value is equal to. Now, one comment on notation here is your textbook uses little p to denote the p-value. I'm not crazy about that notation. The reason for that is we also use lowercase p to denote the population proportion. So whenever I write the p-value, I tend to write p-value. All right, so let's look at an example. So looking at example 1, a sociologist claims that the average number of people per family unit in a large subdivision is higher than the national average of 4.7. He interviews 100 families, obtaining the mean of 4.8 with a standard deviation of 0.8. So if you will recall, we actually already worked this problem using rejection regions. And so that problem was on page 6 of your notes. So take a moment, pause the video, go back and review that problem on page 6. And we're going to make a comparison between these results and the results we found on page 6. So on page 6 we use an alpha of 0.10, so we're going to do the exact same thing here. Now our first couple steps for this problem are going to be exactly the same as what we did on page 6. The first thing we're going to do is set up our null and alternative hypothesis. So under the null we have mu is equal to 4.70, and under the alternative mu is greater than 4.70. And just like before, we're going to set up our test statistic. And so z is going to be equal to 1.25. And you can see how we calculated that again by looking at the page 6 notes. Now, in order to conclude our hypothesis test, what we're going to do is we're actually going to find the p-value instead of the rejection region. So to find our p-value, what we're going to do is first I'm going to draw a standard normal curve, and I'm going to write down the value of our test statistic. Now this is what we call a right-tailed test, so the p-value is going to be the area that falls to the right of this endpoint. So now to find what that area is equal to, you could either use a standard normal table, or I'm going to use my calculator. So using my calculator, what I'm going to do is use the norm CDF function. And I've actually already got these values in here. So the lower endpoint for the area that we want occurs at 1.25, and then the upper I'm just going to set to be infinity. And then we've got mu is equal to 0, sigma is equal to 1, because we're looking at the area under a standard normal curve. And you'll notice that the area here under the curve is equal to 0.1056. So what this tells me is that my p-value is equal to 0.1056. So what this tells me in a probability notation is that the p-value is equal to the probability that z is greater than 1.25, which is equal to 0.1056. So notice, if alpha is equal to 0.10, like in our previous example, we're going to fail to reject the null and get the exact same conclusion that we did on the previous one. On the other hand, let's just suppose that alpha was equal to 0.11. Well, notice in this case, you would reject the null. So this is one reason it's much more informative to actually give the p-value than to just report the alpha at which it was significant. So notice we could conclude this by saying at the 10% significance level, there is insufficient evidence to show that the average number of people per family unit in a large subdivision is higher than the national average of 4.70, and then what I'm going to do is just after this I'm going to say p-value equal to 0.1056. So that way someone reading this, and that's 0.1056, I realize that's not very clear. That way somebody reading this would know not only was it significant at the 10% level, but we get the p-value as well, which is a much more informative conclusion. All right, we've got one more example here, and you'll notice that we've actually looked at this example previously. So if you have a look at page 9, we've already worked this problem, and you'll see it right here. So what I would like you to do for this problem is same thing we did before. I'd like you to find the p-value, and then I'd also like you to find what the conclusion would be at alpha equal to 0.01. And when you write your conclusion, do what we did last time. Write your conclusion like you normally would, but put the p-value at the end. And you'll notice if you look at page 9, a lot of the work is already done for you. So if you want to, when you report this, you can just give me the null and alternative, and then instead of calculating the test statistic, you can just tell me z is equal to, and then reference page 9. But I would like to see how you're calculating the p-value. I'd like to see that curve drawn out and what area under the curve you are looking for. So this is going to conclude the section 10.6 notes.